The purpose of this video is to diagram and explain what happens at an oceanic to continental collision or oceanic to continental convergent plate boundary. At one of these types of plate boundaries, the oceanic crust is much denser than the continental crust, so the oceanic crust will undergo a process called subduction, where it sinks into the mantle underneath the continental crust. The continental crust then gets pushed upwards into mountains over the sinking oceanic crust. Do note I'm saying oceanic crust here, but it's really the whole tectonic plate. So it's the lithosphere that's containing the oceanic crust that is sinking, and then the lithosphere with the continental crust that is overriding on top of it. Let's start with a simple diagram here. I'm going to just draw in the oceanic lithosphere, crust and lithosphere here. So this is going to be oceanic crust and lithosphere, and then we're going to have the continental crust and lithosphere overriding on top of it. And these are going to be the mountains that are forming as a result of that collision. And the artwork is not great. If I ask you guys to draw your own diagrams, I'm not going to be grading you based on your artistic abilities. It's really just based on does the diagram represent what you're trying to show? And the best way to make sure that this works is to label everything. So here I'm going to label this continental crust and lithosphere. And I'm actually going to change the thickness of this pen a little bit so that it's not quite so thick. And then to show you where the seafloor, where not the seafloor, but the sea itself is going to be. So this is going to be the ocean surface. Remember that we have plate convection or mantle convection here that's actually moving the plates. So these plates are going to be colliding with each other. I'm drawing the mantle in green because remember that the mantle is made out of green rocks. So these arrows represent mantle flow in this convection pattern where hotter mantle is rising someplace off of this diagram farther away, and then it gets pushed away from the place where it is rising, and as it cools it sinks back down here, and that's helping to drive this plate motion. As these two plates collide, a couple things are going to happen. So the first is that the oceanic crust here is going to bend downward as it starts sinking into the mantle. As it physically bends downward, it creates a deep part of the ocean. This is called the deep ocean trench. Let me go back to the black here. So this really deep part of the ocean, this is called a deep ocean trench. Geologists usually just shorten this to trench. So in geology, if you see this word trench, it implies a deep ocean trench, and that pretty much always implies that subduction is occurring in that area. So if we see a trench off the coast of a continent or in the middle of the ocean, we can be reasonably sure that subduction is occurring there. The next thing that happens is that as these plates collide with each other, the rocks on the land are going to get crunched upwards and squished upwards, and they're going to become pushed up into mountains. So we're going to get a series of mountains here as a result of those rocks getting crumpled upward, because the plates are pretty strong, and so when they collide with each other, even if we have subduction and one plate being pushed down into the mantle, the rocks on the other side are still going to get crumpled upwards and pushed up into mountains. The next thing that happens here is that as this oceanic crust is sinking into the mantle, it's actually bringing a lot of water with it. Because on top of the oceanic crust here, it's not just the original seafloor rock, but it's usually kilometers thick of sediments, of mud. And hopefully when you guys were all kids, you played outside in the mud and you took a big handful of mud and squished it, and you noticed that water came out between your fingers as you squished that mud. So now we have mud that's getting forced downwards into the mantle, and there's a lot more pressure here, and so all that water is getting squished out of the mud. So I'm going to draw a little blue arrow here to represent water that is getting squished out of the subducted mud. So water gets squished out of subducted mud. And it turns out that when you add water at really high temperatures and pressures, like what we have in the mantle here, then that water gets into the crystalline structure of the rocks that make up the mantle, and it starts to break those crystals apart, and it makes the mantle melt. This is not normally a way that we think of rocks melting, but think of it as adding something to the mantle rocks, which is going to lower their melting temperature. It makes them melt more easily. So this process actually melts the mantle rocks. And that makes magma. The magma doesn't have to have an exclamation point, but magma is always exciting to geologists. So we'll say that the magma has that exclamation point here. So here's my magma in the mantle here. But now this magma, which is liquid, is less dense than everything else around it. So it wants to rise upwards towards the surface. So it rises upwards towards the surface, and eventually it erupts. And when it erupts, it makes a volcano. So we actually get volcanoes as well. We're going to get a whole line of volcanoes. This is going to be called a volcanic arc because it's going to make a slightly curved line of volcanoes on land at the subduction zone. So we're actually going to have two different types of mountains at our subduction zone. We're going to have mountains that are formed just from the crumpling upward of rocks, and we're going to have volcanoes as well. So there are three basic features that we would expect to see on the surface of the Earth that are always going to tell us that this process of subduction is occurring. The first is that we're going to see this deep ocean trench. The second is that we're going to see these mountains. And then the third is that we're going to see the volcanic arc, the row or the line of volcanoes along the subduction zone. These three features together are all a really good indication that subduction is actively occurring in that area. Next, we're going to look at oceanic to oceanic collision. In oceanic to oceanic collision, we still get subduction, but instead of having mountains forming on land, we're going to start out with islands forming, volcanic island arcs. So this is going to be a diagram of oceanic to oceanic collision. So in this case, we're going to have, again, our oceanic crust, which is sinking down into the mantle. My hands are a little unsteady here because I'm trying to avoid hitting the controls on the bottom of my screen. So here we have two pieces of oceanic crust. And note that in this case, they're both relatively thin. So this is going to be oceanic crust. And actually, again, the whole lithosphere. This is going to be oceanic crust and lithosphere as well. One important thing that I want to point out is that there is no rule that like the left side of the plate's always subduct or anything like that. It's always the denser plate. So the denser plate is always going to be subducting, which is almost always the oldest plate. So let's add in just a little bit of context. So we'll add in the ocean surface here. And this is not to scale, so the oceans tend to be about 4 kilometers deep or so in the abyssal plain, so that's basically the regular deep ocean. And remember that the oceanic crust in the lithosphere is usually about 6 kilometers thick, so I've made the oceans relatively deeper than they otherwise would be here. And let's add in the mantle convection. So we have mantle flow here, where it's sinking into the mantle. So mantle flow here, and then again, mantle flow here. And in this case, we still have the deep ocean trench that we saw in oceanic to continental collision. So we still see the deep sea trench, or again, just the trench. And in this case, we're less likely to get really tall mountains or really big mountains forming in the overriding oceanic crust. But we might get some little mountains getting crunched up just from the pressure of these two plates colliding. What we will still have is this water that's getting squished out of the subduction of the subducted plate. And so we still have water, again, squished out of the subducted plate or subducted crust. And this, again, melts the mantle. So this is going to give us the magma forming in the mantle rocks as well. This whole process, by the way, of this water that gets squished out of the subducting crust and melts the mantle rock, that whole process is called, oops, let me go back to my pen. So this whole process is called hydration melting, because the water is hydrating the mantle, and that mantle that's hydrated with the water is going to melt. So they add water to the mantle and we end up with magma. That is called hydration melting. There are a couple other names for it in different geology contexts. For the purposes of this class, if you know it as hydration melting, that is good enough. So that's once again going to result in the formation of melted rock or magma in the mantle. That magma is going to rise up towards the surface, and at first it's going to make a little underwater volcano. So it starts out as an underwater volcano, but as it erupts, more and more material, so it's just going to keep erupting over and over again, and eventually it's going to erupt so much material that it grows up to be above the ocean surface, and at that point it becomes a volcanic island. And again, we're going to have a whole row of these, so just one of them is going to be a volcanic island. The whole row of them is going to be the volcanic island arc. So the main features that we would expect to see at an oceanic to oceanic collision zone are going to be the deep sea trench and then the volcanic island arc. So if we see these features out in the middle of the ocean, we can be pretty sure that oceanic to oceanic collision is occurring there. We'll look at some examples of where this happens around the world in a little bit.